Welcome. Let's discuss the binomial expansion theorem. When we take a look at our first expression, x plus y raised to the 0, well, anything raised to the 0, it is equals to 1. So let's just write that down. We move on to the next expression, x plus y raised to the first. Well, anything raised to the first is itself. So this is equals to 1x plus 1y. But when we get to example C, we're actually going to do some work because x plus y raised to the second, that's the same as x plus y multiply 2 times. And if we wish to expand it, we have to perform some distribution. So let's distribute the value of x. Now we're going to get 1x squared. Let's distribute x to the y. Now that we're going to get xy. Now let's distribute the y with the x. We're going to get another xy. And when we distribute y times y, well, that is y squared. Notice that within this expansion, we can combine these two terms. So now we're going to obtain 1x squared plus 2xy plus 1y squared. So let me just write down the result. When we get to example D, we want to multiply x plus y 3 times. But we know that when I multiply just 2, we have that result. So let me just substitute that as a shortcut. So now let's expand it by performing some distribution. Well, let's see if we can simplify this a little bit further by trying to combine like terms. And here we have some x squared y and 2x squared y. We can combine them as 3x squared y's. In addition, here we have other like terms, xy squared and xy squared. So when we add them up, 1 plus 2, that is 3xy squared. So now let's bring down the y to the third because we didn't combine it with anything. So after the distribution, we obtain the following result. So let me just write down the result. Now when I get to example E, I would have to multiply x plus y 4 different times. That's going to be a lot of work if we want to distribute as we did with the previous examples. So how about if we stop our calculation and let's try to see, is there any relationship between the results that we obtain and the values in Pascal's triangle? In example A, we were raising our exponent to the 0 value. Well, when I take a look at the 0th row, notice that the value, it is equivalent to 1. In example B, we were raising the expression to the first. Well, notice that when I take a look at the first row in Pascal triangle, the first value in our Pascal triangle, it is the first value in our expansion. The second value, which is also 1, it is the next value in our expansion. And by value, I mean the coefficients of every term. When I was raising my exponent to the second, and I take a look at the second row in Pascal triangle, notice that the first value in this row, which is of 1, matches up with the first coefficient in my expansion. The second value in this row, which is of a value of 2, notice that is also matching with the next coefficient in our expansion. And the next value in Pascal triangle in the second row, it matches with the next value in the following term in the expansion. When we're multiplying to the third exponent, and I take a look at the third row in Pascal triangle, we have the same relationship. The first value in the third row matches up with the first coefficient in our expansion. The next value of 3, it matches up with the next coefficient in our expansion. The following value in Pascal's triangle, which is also a 3, matches up with the next coefficient in our expansion. And the next value that follows in Pascal triangle matches up with the last coefficient in our expansion. So now, if we want to expand this expression to the fourth, when it comes to coefficients, what we can do, we can just get all those values from the fourth row in Pascal triangle. So we're going to get a coefficient of 1 and then some space, and then followed by the next coefficient, which is 4, and then followed by the next coefficient, which is 6, followed by the next coefficient, which is 4, followed by the last coefficient, which is 1. So at least when it comes to coefficients, we can always obtain them from Pascal triangle. Now let's discuss the variables in the expansion. And for that, I want to concentrate on example D. The pattern is more clear here. X is the first term in our expansion. And when I identify where X is located in every single term in our expansion, notice that there's a pattern with the exponents. In our first term, X was raised to the third. In the next term, X is raised to the second. And in the next term, X is raised to the first. And on the last one, X is actually raised to the 0. That's why we don't see it. So notice that as I keep moving to the right, the exponent, it decreases by 1. So now when it goes to example E, when I put down the variable of X, I'm going to start by matching the exponent that we had, which is 4. And now for the next term in our expansion, I'm going to decrease by 1. Now we're going to have an exponent of 3. Then the next one, I'm going to decrease by 1, exponent of 2, exponent of 1, exponent of 0. Now when it comes to the variable of y, notice that that's the second term in our expansion. Now if I take a look at the exponents in the opposite direction, going from the right to the left, I have the same pattern. I start with the exponent of 3, and then it decreases by 1. The next exponent is 2. The next exponent is 1. And the last exponent is 0. That's why we don't see it. So we can take advantage of that, because now, let me write this down, as I move from the right to the left, the exponent, it decreases by 1. So on the last term in the right, I'm going to write down y to the fourth. And the next term on the left, I'm going to decrease by 1, y to the third. Then the one that follows, y to the second, y to the first, y to the 0. So we are done. So now let's just clean this up a little bit. My first term is just going to be 1x to the fourth. Then the next one is going to be 4x to the third, y. The one that follows, 6x to the second, y to the second. Then 4x, y to the third. And lastly, 1y to the fourth. Let me just write down the result. And this relationship that we have just observed is what we define as the binomial expansion theorem. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.